This video tells you the relationship between a complex analytic function and a conformal map. If you haven't watched the conformal mappings video that I recorded, go do that now, because otherwise this video won't make much sense. But here's the takeaway. This is the key theorem. If f is a complex analytic function at z equals z naught, and f prime of z naught is not zero, then f is conformal at z naught. Recall that conformal mappings are local. It's a local property, which means it only depends on the derivatives, and in particular only depends on the Jacobian matrix of f, as in the matrix of partial derivatives of both components of f. Now, since f is a complex function here, it has real and imaginary parts. Those are the two components that we're talking about. Okay, so in order to see how this works, we really basically need to make use of nothing other than two little facts. One is how tangent vectors work for curves and paths in the complex plane, and the other is the complex chain rule. Put those together with how angles work and arguments work, and you're all set. So let's see how that works. So first of all, if P, and I'm going to go from R to C, P is a path in complex plane, P of T is equal to, well, it's got a real part, and it's got an imaginary part. For all intents and purposes, you could think of this as a function x and a function y. Okay, now given this complex function, you can ask, well, what is its tangent vector? Its tangent vector is p prime of t, and that's simply just the derivative of these two components. Now, this is a vector in R2, and it's a single complex number as well. Now you might ask, okay, graphically, here's my real part of z and my imaginary part of z. If I'm at some point p of t, the tangent vector is going to be pointing off like this. That's a complex number. And wouldn't you know, that complex number has an angle. That angle, theta, is conveniently the argument, p prime of t. So if I want to find angles in complex numbers, it's actually quite easy because they're sort of built into the way that we do the complex algebra. Okay, sounds like a plan. Now, if you watched the video on conformal mappings, you'd know that we learned how to transform angles and tangent vectors using the function f. So if f is a complex function, then if I want to know what is d by dt of f of p of t, well, the chain rule will have us do something like f prime at p of t times p prime of t. And as before, you'd realize that this p of t guy is a vector, but p prime of t is also a complex number. as is this. This is also a complex number. And one thing that you should now realize is multiplication by a complex number does two things: rotation and scaling. Those are the two things that give rise to a conformal mapping, provided this guy is not 0. Well, let's see how that works. So what's the angle? The argument of d by dt, the transformed angle, that's the argument of f prime of p of t times p prime of t. Now, if you remember, arguments are angles, and they're exponents of e to the I something or other. So that means, in particular, that they add. This is the original angle of the path. Of course, this is the transformed angle. And so all that the transformation does is it applies a rotation. Provided f prime is not 0. All right, so now we're in position to check conformality. If I have two paths, P and Q, what happens? That intersect at T. I've got P and I've got Q. Here's my P prime. Here's my Q prime. The angle that P prime makes with the horizontal axis, draw the horizontal axis in red. The angle that P prime makes, that's the argument of P prime. The angle that Q makes, that's what? That's the argument of Q prime. So the angle between these two guys P prime and Q prime. In general, if we're in the plane, we have to use this awful arc cosine formula, but here in complex numbers we don't. We can just use the arguments. It's actually very easy. It's just the argument of Q prime minus the argument of P prime. And that's it. Sweet. So what happens to the transformed angle between these two curves? Well, it's the angle between, it's the transformed angle of angle P prime minus transformed angle for Q prime. Well, we now know what that is. That's d by dt, or rather that's the argument of d by dt, of f of p t minus argument d by dt of f of q of t that's the argument of f prime at p of t plus the argument of p prime, that's this first one, minus argument of f prime at p of t of q of t rather. Getting ahead of myself slightly. Plus the argument of q prime. Both of these of t. But the curves intersect at t. Therefore, these arguments of f cancel out. And just to make that really entirely clear, let's rewrite it as such. So now these guys definitely cancel, and I'm left with the original angle. Okay, and in fact, that calculation is the end of the proof. That if I have a complex analytic function, it has an f prime, and that f prime is not 0. When its f prime is not 0, then this exists at all. F prime of p of t is not 0. If it were equal to 0, it doesn't have an angle at all. The argument is not defined. But it is defined because the derivative is not equal to 0 there. And that ends up establishing that just what we wanted. So complex analytic functions, when their derivative is not 0, preserve angle. So now it allows you to ask really basic questions about, hey, where are various mappings conformal? So for instance, example, f of z equals z squared is conformal for all z not equal to 0. Why? Because f prime of z is just the usual 2z. That's not 0 whenever z is not 0. Of course, you could cook up lots more conformal mappings this way. So this is actually a very convenient way to find conformal mappings. Just find complex analytic functions, find where the derivatives don't have zeros, and you got a conformal map. And that's the end of the story.